And we'll start the proof by considering a picture of our region, some region in 3D where inside this region we're saying that f is path independent. And we'll consider two paths inside this region, say one path from A to B here, and we'll consider another path from A to B prime. And alright, this is all inside some three-dimensional region omega. And this proof is going to rely on exactly this idea. So we want to first start off by making our first assumption, which is that I assume that the line integral of f dot dr is path independent. And our goal now is going to be to find, and we have to find some phi such that f can be expressed as the gradient of that phi. So this is our goal for this proof. And when we go through and do this, think about how exactly we should be doing this. And the idea here is that, well, we know that due to the path independence, we're trying to write f as the gradient of some scalar field. So we want to see how does this imply that f is conservative, saying that f is p of x, y, z I plus q of x, y, z j plus r of x, y, z k. And the question is how to find a suitable scalar function phi such that d phi dx is equal to the function p, d phi dy is equal to the function q, and d phi dz is equal to the function r. And the idea here is to recall what the definition of the limit is, right? And specifically, we recall that, say, well, I'm just going to do this for the x partial derivative. So for the first component, the x component. The idea, though, is that this argument applies in general regardless of the component. You can always make this almost exact same argument for either component. So let's say that b and b prime look like this. They're along the x-axis. And recall that actually if we denote the point b as the point x, y, z, and b prime as the point x plus h, y, z for some value of h, right, we have that the partial derivative of phi with respect to x is exactly, by the definition of the partial derivative, the limit as h goes to 0 of phi of x plus h comma y comma z minus phi of x comma y comma z divided by h or equivalently the limit as h goes to 0 of phi of b, the scalar function at b, minus the scalar function at b prime, divided by h. So remember, this is the definition of the partial derivative of any scalar function. And the idea here is that we're looking for the way forward for defining, right, this phi function. So without loss of generality, let's go through and do this. We'll define this phi function. We'll define the function phi of the point B, or the function phi at the point B, to be exactly the line integral from a to b of f dot dr. We can make this definition exactly. And if we define this function phi of b to be the line integral, there's no problem with doing that. Right, we then have the definition of the partial derivative, right, d phi dx, which gives us the following. And we don't even have, before we even use this partial derivative limit, we have that if you just consider phi at b minus phi at b prime, this is the same thing as the integral from a to b of f dot dr minus the integral from a to b prime of f dot dr, which from our simplifications for line integrals is just the line integral from the point B to the point B prime, from the point B prime to the point B. This is the same thing as the line integral from B prime to the point B. And the key thing here is to exactly now consider this definition of the partial derivative. We're going to use the actual exact definition of the partial derivative, because with this definition for this potential function, if we say that for some point B and some point A, we define the potential function as being equal to the line integral of the vector field from A to B. Then for any other point B prime, phi of B minus phi of B prime is just going to be the line integral from B prime to B. And now remember, we've assumed path independence, so the path going from B prime to B doesn't matter taken when evaluating this integral. Right? Any path from B prime to B will be the same value of this line integral because of path independence. So what we'll do is we'll consider the simplest possible path from B to B prime, which is exactly a straight line. So we'll consider the straight line path along the x-axis from B to B prime, where we'll call this distance right here h. Or this distance is going to be not h, but it's just the distance of this straight line, which we can definitely parameterize, so that this distance right here is equal to h. So let's put h right here. And so then what we have is the following expression. We have that first off, from the partial derivative, the expression for the partial derivative, d phi dx is equal to this limit right here which is the same as the limit as h goes to 0 of the integral from b prime to b of f dot dr divided by h. And if you recall, you'll remember that this is the same thing, right? We're using the definition of the line integral as saying that d phi dx is equal to the limit as h goes to 0 of, we'll parameterize our curve with parameters t going from 0 to 1 of f of r of t dot product with r prime of t dt all divided by h, where r of t is the curve, or specifically the straight line from b prime to b, which is exactly equal to the line that at t equals 0 starts at b prime and passes through the point b. So it's equal to at the point x, y, z plus h times 1 minus t 0, 0. And this is for t from 0 to 1. And this works because this is exactly giving us all of the points on this line right here from b to b prime. Not only that, but we can calculate the tangent vector to this line r prime relatively easily, taking the derivative here, which gives us negative h times 1, 0, 0, or negative h times I hat. And if we plug in to this equation, then this becomes the integral of f of r. Remember, f of r of t is the same thing as PQR, all evaluated at r of t. And this is the dot product then with r prime, which is negative h times I dt. Well, the h is constant in this integration with respect to t, so it comes out and cancels with this h. And what we're left then is d phi dx is equal to the limit as h goes to 0, integral from 0 to 1 of the dot product of this with I hat is going to be p, the negative sign on the outside here. So this is going to be just p of x of t plus h times t, or not x of t, just x plus h times t. Because that's the x coordinate of the point B. And then y, z, dt. And this is where we want to use one of our theorems from Calculus 1. This entire thing is just a nice function of t, and we can use the mean value theorem from Calculus 1 to assert that there's going to be, and this is because this is a continuous function. P is a continuous function of all of its arguments. So at any point x, y, z, it's a continuous function of the x argument, and therefore this composition is continuous. And by the mean value theorem, there exists some value t star such that the following is true. d phi dx is going to be equal to the limit as h goes to 0 of this function evaluated at t star multiplied by the size of the domain. And so d phi dx is equal to the limit as h goes to 0 is negative 1 of p of x plus h times t star y z. And the last thing to note here is that t star is between 0 and 1, so as h goes to 0, right, t star is constant. This is a continuous function, and therefore this is going to be the same thing as being equal to negative p of x, y, z. And the conclusion here is that we can do the exact same thing for the y-axis and the z-axis as well. So using the exact same method and the exact same idea, we can go through and show that d phi dy is equal to negative q of x, y, z at every point in this domain, and that d phi dz is equal to negative r of x, y, z. And so therefore, the vector field f that we started with will in fact be equal to the gradient of phi, and you have a negative sign here, but you can just recall this. This is the same thing as saying that it's equal to the gradient of psi, where psi is negative times phi. So the point here is that we've shown that this is in fact a conservative vector field, and we've proven the theorem. But the idea here is that the main use of this statement is that if the line integral is not path independent, then f is not conservative. And we can actually use this very, very nicely. We can use this directly to find a counterexample to the one of the theorems that we talked about before. So let's take a look at the vector field given by 2D y over x squared plus y squared times negative 1 plus, or in the y component is going to be x over x squared plus y squared. So one of our main things to look at here is to look at the curl of the vector field f. And sure enough, if you take the curl of this vector field, you're going to get that it's equal to 0. Right? It's always important to look at the curl and the divergence of a given vector field. But so you want to check this. Go through and check this calculation right here. I'm not going to do it, but it is similar to some of the homework problems. And you'll remember that we had that previous theorem that was proven that said that, so recall, if the vector field f is conservative, then the curl of f is equal to 0. And I told you to be very, very careful about using this theorem. It's only it's a one-way theorem. You can't go backwards unless some suitable restriction is made to this statement. And this is a great example of a field for which we have to be very, very careful because the curl of this field is equal to 0. However, if we go through and look at the line integral, And if I am very, very careful here, this is, we'll see here, I can give you a hint of why things are not going to work out so nicely for this field. Right? This field is only, it's not defined at the origin. If you take the limit of either of these two component functions as x goes to 0, 0, you'll see very clearly that we have to remove 0, 0 from the domain of this function. So what this looks like, if we kind of plot this out, is that we have some hole at the origin. And that being said, we can still visualize this vector field very, very nicely, and we can do that in Python just by taking a look at the Python window. And running our visualization. So like this is what this vector field looks like, and you can definitely see that it is, sort of, it looks like it's rotating around the origin, this origin point right here. So initially you would expect that the rotation of this vector field is non-zero, but we just showed the curl of this vector field, and that's what you should go through and do. Take the derivative and show that the curl of this vector field is equal to 0. So technically it's irrotational at any given localized point. This is a little bit confusing, and it looks a little bit confusing. And the way out here is to kind of take this idea and let's consider two separate paths. And we'll consider a path that surrounds the origin and a path that is away from the origin. And you can do this with any path, but we'll just use a circle. So we'll have two separate circles. This is our path 1 that surrounds the origin, and this is our path 2 that is separated from the origin or away from the origin. And what we'll also consider is that the tangent vectors to the curve, to each one of these curves, combined with the vector field at those points on the boundary of this curve. So if we do a plot of that, this is what we see right here. Each one of these curves, where in red here is the tangent vector to the curve, and in blue is the actual vector field at each one of these individual points. And you see that for like this curve right here, the vector field is pointing in all sorts of different directions depending on how the curve is rotating compared to the tangent vector, because this path is moved away from the origin, and this path is centered around the origin right here. And let's consider this at a whole bunch of very small points. The magnitude of this projection, the dot product of the vector field at each point on the curve, and the tangent vector at each point on the curve, and make a plot at each point of what this value is. That's what this looks like right here. I'll make it even bigger so we can kind of see this right here. It's a little bit out of scale when I do that, but you can still see what we're talking about. So this projection, right, and this is the color bar. So each one of these colored points on each one of these curves represents the value of the dot product of the vector field and the tangent vector at each one of those points. And you see that this curve right here that's going around, right, the origin has a relatively constant value here around 0.9, right, which is the constant value of the dot product of the vector field with the tangent vector, right, which is definitely due to the fact that this vector field is circularly symmetric, or symmetric around this point. But alternatively, if you look at this plot right here, you see that the maximum value for this dot product is around a little bit over 0.25, or this high yellow value right here. And then gradually, right, as you rotate around the vector field, well, this right here, you're starting at around 90 degrees, so you're around 0 for the actual projection. And as you move around, you get to a maximum value of around 0.25, which corresponds to the vector field pointing essentially, it's pointing along the curve in the direction of the tangent vector. And then as you move in this direction more and more, you get closer to 0 because the vector field is getting closer and closer to tangent or perpendicular to the tangent to the curve, until the point where you're here and the vector field is pointing in a different direction than the tangent to the curve. This is why it gets all the way down to around negative 0.75 right here. And this, I think, is a very, very nice picture because it clearly shows that even in this small portion right here on the curve, the maximum projection gets, or the minimum projection gets to a value of negative 0.75 on this curve, in this about a quarter of the curve right here. And then for about 3/4 of the curve, right, the maximum projection gets to around 0.25 right here. And this is actually hinting at something extremely kind of neat, right? If you go through and do the line integral around any path, actually, you'll be able to show that when you move away from the origin, the line integral around this vector field around any path is going to be 0, right? So, like, say, if we consider like just a domain out here, where any path inside that domain that's away from the origin, the line integral will be 0, and therefore this function will be conservative on any region that does not contain the origin. However, right, the line integral around this path right here is clearly going to be non-zero. It's not going to be equal to 0. So the origin is our problem point for this this expression, for this example, and we're seeing now that this picture is clear enough evidence that this vector field is not conservative, and we'll see that exactly in the following. So if we go ahead and open up this plot again, we know that we have a vector field here that's rotating around the origin, and we'll consider the line integral just around a path, say, that contains the origin, and we'll stick with a simplified path of radius epsilon, so a circle of radius epsilon. The line integral on this path is going to be line integral on C, or from, we'll say C from the circle, it's from 0 to 2 pi of f of r of theta dot product with r prime of theta d theta, where r of theta is epsilon cosine theta, epsilon sine theta. If you want to think of this as in 3D, with 0 here because this is just a two-dimensional vector field. R prime of theta is going to be negative epsilon sine theta, epsilon cosine theta. And when you plug in to find f of r of theta, that's plugging r of theta into the vector field f, this is equal to negative epsilon sine theta And x squared plus y squared will just be epsilon squared. We'll have epsilon sine theta. It'll be positive epsilon cosine theta. That's this x, the x coordinate, over epsilon squared. And then 0 is the third component. I guess really we don't have to consider the third component until we consider the curl of the vector field. That's just making things a little bit too messy. So f of r of theta is just going to be negative sine of theta over epsilon cosine of theta over epsilon. So when we go to evaluate this line integral, this becomes the integral from 0 to 2 pi of this vector negative sine theta over epsilon cosine theta over epsilon dot product with r prime, which is negative epsilon sine theta cosine theta. And going through and doing this integral, well, when we do the dot product, we multiply these two things together, we get sine squared. We multiply these two things together, we get cosine squared. So the resulting epsilon over epsilon is 1. So we're just going to get this thing right here as sine squared theta plus cosine squared theta, which is equal to 1. So this is the integral from 0 to 2 pi of 1 d theta, which is 2 pi. Right, so this value, the value of the circulation around this circle, is in fact just equal to 2 pi. That's the circulation of this vector field around the circle of radius 1. And now this is it. This shows us that this vector field f cannot be conservative on the indicated domain, because we found a closed path, and I held off from writing this and mentioning this because I wanted you to think about it, but this path C is a closed path. Right? It's the circle of radius epsilon, which is a closed path. This is a closed path that's giving us a non-zero line integral, right? And what that means, going back to our theorem, is that this is not path independent, because we have that the line integral along any closed curve C should be equal to 0. And I forgot to write this equal to 0 along any closed curve C implies path independence. What this means is that because we found a path for which it's non-zero, then this integral is not path independent, and therefore, because it's not path independent, the function is not conservative. So there exists no scalar potential function phi to express this vector field as the gradient of that scalar potential function. And what we're going to do is we're going to investigate and see, right, why this by implication actually does hold, right? And we're going to kind of investigate exactly what it is that's failing here. And you probably, if you're thinking about the origin, you're right. The idea here is that this vector field in this domain that we're looking at is what's called a multiply. It's not a simply connected domain. It's what's called multiply connected. Right? There's a hole or a missing point in this domain. This is actually a very, very deep result topologically, and goes to a very deep area of differential geometry known as de Rham cohomology. So we won't be talking about much of that here, but it is very, very important to point out. And the idea here is that we're seeing that this we have to be very, very careful with statements like this, because this is saying if f is conservative and the curl of f is equal to 0, you can't go backwards. We'll see that you can go backwards on a simply connected domain, right? So if we add to this statement that if f is conservative on a simply connected domain, it's going to turn out that this becomes an if and only if statement. But this example very clearly shows that it's not an if and only if statement unless we include certain restrictions on the domain. So let's write down the statement of this theorem, which we won't be able to prove yet, but we'll prove it once we end up showing what's called Stokes Theorem. So we're going to say let omega be a simply connected domain in three-dimensional space, and we also have that an analog of this theorem holds, right, in 2D as well. We'll see that as a special case. Then we have the statement that f is conservative in omega in 3D or D in 2D if and only if the curl of f is equal to 0 at every point in omega, or f is irrotational. In omega. So this is a big theorem, and it's saying it's very, very important that we've seen from the previous example that this region be simply connected, a simply connected region. But if this is the case, then we do have the by implication of this statement right here, our previous theorem on conservative vector fields, which is really nice and very, very useful. But we can't prove this yet. The proof is going to come from what's called Stokes Theorem. But right, if we move back to our previous example, we see that this is very, very nice. So like that previous example on gravity, we had that the force vector was negative mg k hat, and we know that this vector, you can say that, well, if you just take the curl of f, this vector is defined everywhere on all R3, and the curl of this vector field is definitely equal to 0. Right, because this is a constant vector field, so therefore, because the domain of the vector field is simply connected, right, by that theorem, then f is conservative. So it's important to emphasize here that simply connected means with no holes in the domain. Or another, equivalently, you can think of it as any closed loop can be shrunk down to a point inside the domain. Another nice way of thinking of it. But the idea here is that this theorem only works if the domain is simply connected. But for the previous theorem, or the previous example, it doesn't work because there's one hole in this domain, and just because the curl of this vector field is 0 doesn't mean that it's a conservative vector field, and we definitely showed that because we found a path for which the line integral was non-zero, a closed path for which the line integral was non-zero. So the last thing that we want to look at here is that, well, if we have a given vector field and we somehow, we know that it's conservative, or we suspect that it's conservative, how could we recover the potential function? So given a vector field F that is curl free on a simply connected domain, how can we recover the scalar potential? So for example, we'll start with the following vector field. F is equal to cosine of y 1 minus x times sine of y, and we'll say that the z coordinate is equal to 1. Alright, so if this is conservative, it certainly has, it's continuous everywhere. Each one of these functions is continuous. Right? It's defined on all of R3, so there's no holes, and the domain is simply connected. So this is a continuous, and it's actually infinitely many times continuous. You can take the derivatives of this vector field infinitely many times, but the main thing is that it's continuous on a simply connected domain. And if you go through and evaluate the curl of this vector field, curl of this vector field is going to be, this is P, Q, and R. Curl is going to be the y partial derivative of R minus the z partial derivative of Q. It's going to be the x partial derivative and negative times the x partial derivative of R minus the z partial derivative of P, and the x partial derivative of Q minus the y partial derivative of P. So dr dy is d1 dy, which is 0. And then dq dz is going to be the partial derivative of this function with respect to z, which is also 0. dr dx is going to be 0. dp dz is going to be the derivative of cosine of y, partial derivative with respect to z, which is 0. And then dq dx is going to be negative sine of y, and then minus the y partial derivative of p. Y partial derivative of cosine of y is negative sine of y. So this becomes sine of y minus sine of y, which is also 0. So this is exactly equal to the 0 vector, because this function is defined and it's continuous on a simply connected domain. That means that this function is conservative. And remember, we have not proved that yet, but we will get there in subsequent lectures. We get to Stokes Theorem. And the idea then, and what's really nice about this is that, so we know this is going to be equal to the gradient of some phi. So this vector field PQR will be equal to, right, P is the x partial derivative of phi. Q is going to be the y partial derivative of phi. And R is going to be the z partial derivative of phi. The question is how to solve for this phi. So we'll go through and integrate one of these equations to try and see what happens here. So what we're going to do here is we just consider the integral. So we know that the indefinite integral of the partial derivative of phi with respect to x, we integrate this with respect to x, this is the same thing as the integral of the function p with respect to x. And we know that this is going to be equal to, in general, phi itself. And this becomes the integral of p dx plus, in general, it's not going to be a constant. It's going to be a function of x and y, or a function of y and z. So in general, right, when we integrate both sides of this expression right here, we have to include not a constant, right, because we're only integrating a partial derivative. But if we go through and check this, right, we'll see that this works out really nicely. Because if you take the partial derivatives of both sides of this expression, what you're going to end up getting is the partial derivatives. This is just kind of a check over here. I'll do it over on the right to show that this is making sense. When you take both the partial derivatives of both sides of this expression with respect to x, you get the partial derivative of the indefinite integral of p dx, which is just going to be equal to p itself, plus the partial derivative of a function of y and z, which is going to be equal to 0. Right, so this is giving us exactly this the first component. This is important because it's kind of like, it's exactly what you would expect from a single variable calculus course, but you have to be very careful here. This f of yz is in general a function of y and z that's unknown, but we have to solve for. So specifically, this is telling us then that phi is equal to the integral of p, and p is the function cosine of y. Dx plus some function of y and z. So phi is equal to, well, the antiderivative of cosine of y with respect to x is just x times cosine of y. So this is really the first step that we've verified what we need to know about getting this first step in satisfying, right, the first component of this equality right here. So we still don't know what f is. We have to go through and solve for f. And we'll do that by using our second condition, which is that the y partial derivative of phi has to be equal to 1 minus x times sine of y. And if this is our equation for phi, which it has to be if the first equation is satisfied, right, we have to take the y partial derivative of this, and this is going to say that, well, the y partial derivative of x times cosine of y is negative x times sine of y plus the y partial derivative of f, whatever that is. And this gives us a very nice equation, and gives us the equation that the partial derivative of f with respect to y is equal to 1 if we add x times sine y to both sides of this expression. So we can do the same exact thing here to get, we can take the antiderivative of both sides of this expression, right, to get that f itself has to be equal to y plus some general function g of z. Right? Because if you take the antiderivative of both sides of this expression with respect to y, you get the antiderivative of the partial derivative of f with respect to y dy. So if we take the antiderivative of the left-hand side here, you get the antiderivative of 1 is going to be y plus some function g of z, general function that we don't know yet, we have to solve for. And the antiderivative of this with respect to y is just going to be f. This function g of z is determined, right, by the third condition. You can check this, right? If you take the partial derivative of this expression with respect to y, on the left-hand side you get df dy, on the right-hand side you get 1 plus the y partial derivative of g of z, which is 0. So it's recovering this right here. But this expression for f inside this expression for phi will give us another simplification. We have that it's equal to x cosine of y plus f, which is y plus g of z. And we're almost done here, because this expression for phi will satisfy the first two equations in our system here for the conservative vector field f. So the last equation that we have to make sure is satisfied is that the z partial derivative of r is, or the z partial derivative of phi is equal to r. So d phi dz is equal to r, which is 1. And with f being equal to this, d phi dz is going to be, well, the z partial derivative of this is 0. The z partial derivative of y is 0. So we're just left with g prime of z. The z partial derivative of g of z is g prime. And if we take the integral of both sides of this equation with respect to z, or the antiderivative, this is equal to 1, and so we have that phi we'll just use the first and second here, so that the integral of g prime of z, antiderivative of g prime of z is just going to be g of z, and this is going to be equal to the z integral of 1, which is going to be 1, or it's going to be z times plus some constant. This is just from calculus 1. So we have g of z, and therefore our function, our potential function, which is a function of x, y, and z, or just a function of position r, is going to be exactly equal to x times cosine of y plus y plus g of z, which is z plus a constant. and this right here is exactly the correct expression for phi. So we've solved for our scalar potential function, and it's always going to be determined up to an additional constant because of integration. It's the same thing as for single variable functions. A good problem for you to look into is sort of a change in this problem just a little bit, right? What happens if we spoil this problem? So let's change the system a little bit. We'll say, what if we investigate the vector field f equal to cosine of y plus z 1 minus x sine of y and 1 cell. So first things first, if you take the curl of this vector field, you'll see that it's not curl free. It's not equal to 0, the curl. Therefore, it's not conservative. But nevertheless, you can try and proceed similar to how we proceed here, right? And going through and solving for that potential function. And this exercise is a good exercise because what you're going to want to do is try to find a contradiction. So try to find why f itself cannot be equal to the gradient of phi for any scalar potential for this example. But this will end the lecture for today. This is a very, very important topic, and what we'll be moving into in the next lecture is going to be the definition of what's called a surface integral. So thank you very much for listening to lecture today, and I hope you have a great day.